All right, welcome back. Today we're going to talk about uniform distributions, and now that I'm done saying the title, I feel like the lesson's about almost half over. This is probably the shortest lesson of the year, so I won't drag it out any longer than it needs to be, give you a little bit of a break today. Okay, the idea of a uniform distribution is really just where every single possible outcome is equally likely. So when you go and graph it, or you look at the probabilities, you get the same probabilities for every possible outcome, and the graph basically just looks flat. Um, don't worry too much about whether that's supposed to be a histogram or a bar graph. It's just a really crappy graph to begin with, but it kind of gives the point that every single die roll, whether it's 1, 2, 3, 4, 5, or 6, has an equally likely chance of occurring, that probability being a 1 in 6 chance. So as it turns out, we can simplify our math here by using that equation. The probability of any given outcome occurring is equal to 1 over n, where n is the number of possible outcomes. Notice that this formula doesn't have an x in it, and it's because it doesn't matter what the value of x is, you get the same value every time. So whether I'm rolling a 1 or a 2 or a 3, doesn't matter. The probability of it occurring is 1 out of 6. Going back to the dice example. So that makes our life really easy. What we're going to do now is just try and see how it works in an actual practical problem. So for example 1, by the way, example 1 is the only example, so we're going to go through this pretty quickly. In a casino game, you draw a single card from a deck. If it's an ace, you win $50. If it's a face card, you win $25. If it's any other numbered card, so 2 through 10, then you win the value of that card in dollars. So if you draw 7, you win $7. If you draw 3, you win $3. What is the probability of drawing any given card? Now, the probability of any card. Now this one is a little bit trickier to write in proper format using the kind of x equals x thing, because the numbered cards are all different outcomes. The cards themselves are all different outcomes, but they're not numeric in value. Like Jack of Hearts is not a numeric value. So we're not going to worry too much about that. And we're just going to say the probability of any card is 1 out of 52. So what is the expected value that you'd win by playing? Remember expected value. I'm going to use W for expected winnings, since that's really what we're looking for. This is just going to be the sum of a whole bunch of terms, and each term is going to be the outcome times the probability that it occurs. So now in this case, I'm not saying the outcome is, Jack of Hearts or Queen of Spades. What I'm saying is the expected win is going to be $2, $3, $10, $25, or $50, that kind of thing. So in this case, we're going to get the expected winning of $50 if it's an ace. So the outcome is 50, and the probability of it occurring is actually not 1 out of 52, but 4 out of 52, because there are 4 aces. And we're going to actually simplify this down a little bit and just think of it as being 4 identical suits, because that's what it is. So an ace is going to be a 1 in 13 chance of happening. And then I win $25 if it's a face card. Well, the face cards have a 3 in 13 chance of happening. And then if it's not either a face card or an ace, it's the numbered value. So there'll be 10 times 1/13 plus 9 times 1/13 plus 8 times 1/13 all the way down to 2. 2 times 1/13. Now, I'm not going to write them all there. You'll notice I left out the 7, 6, 5, 4, 3 just because of space. But the ... I think the pattern's pretty obvious on this one. Now, something that's nice about this is that I can actually factor the 1/13 out of all of them. You don't have to do this. At this point, honestly, it's algebra. There's no more data management involved. It's just algebra. You can work this out however you want. I think it's faster to pull out the 1/13. And then I'm left with 50 plus 25 times 3, because there was a 3 out of 13 chance of getting a face card. I could have done it as 1 out of 13 of chance of getting a jack for 25, a 1 out of 13 of getting a queen, a 1 out of 13 of getting a king, but it's just easier to put them together. And now I want to add up the numbers 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2. And I'm going to remind you that I can actually take a little shortcut here because we learned how to do summations back in Unit 3. And if I want to add all the numbers from 10 down to 2, the two end numbers, 10 and 2, will total 11. 9 and will total 12. 9 and 3 will total 12. 8 and 4 will total 12. And since there are 9 numbers, I'll have 4.5 pairs of 12. So 4.5 times 12 is 48, 54. Now again, you could just manually do that one. So if you don't like the way I just did it, do it manually by all means. And then from there, I'm just going to add up the 50 plus 75 plus 54 is 179, which becomes 179 over 13. And that equals $13.77. So if you played this game a bajillion times, on average, you would win $13.77. The last thing I want to mention here is that this question seems pretty straightforward. However, there's a definition in here I want to make sure that you're aware of, and that's this word right here. What it is to be fair. So for instance, you might say, well, if they charge $10, it's fair because then I'll win money more often than not. Well, that's fair for you, maybe, but it's not fair for the casino. And if the casino charges you $20 to play, you could argue that it's not fair for you, despite the fact that they might say it's completely fair for them. So in data management, fair means that the expected value to play is the expected value of the winnings is equal the amount that you pay to play. So if you want this to be fair, they should charge the exact same amount as the expected value. Now, of course, that's fair in the mathematical definition or sense of the term. It's not necessarily fair in real life where you're walking to the casino to have a good time. If the casino's odds of basically if they're giving away an average of 13.77 per game played, but charging 13.77 per game played, they're going to lose money because they still have to pay people to deal the cards and man the stations and the lighting and property and all that stuff. So they of course do have to charge money to make a profit, the same as any other business. So that might be fair to charge more than that in real life, but as far as mathematical definitions concerned, fair means that neither player holds an advantage to win money in the long run. Now, just before I finish off, I do want to just dig one more thing into fair that is often a misconception. Fair doesn't mean the probability of winning and the probability of losing is the same. It has to do with expected values on both sides. So, for instance, if we played a game where I said, okay, let's flip a coin. That's a 50-50 chance that I'm going to win, 50-50 chance that you're going to win. That sounds fair. So if I flip a head, I'll give you $2. And if I flip a tail, you give me $100. 50-50 chance of winning sounds fair. But obviously, I'm going to win a lot more money in the long run if half the time I'm taking $100 from you and half the time you're taking $2 from me. Now, if we played a game where, for instance, we rolled a die, and if I roll a 6, if I roll a 6 on a die, you give me $10, and if I roll any other number, I'll give you $2. So you have a better probability of winning. I have a probability to win, or I have a chance to win more money when I do win. And if you actually work it out, 1/6 of the time I'm going to take $10 and 5/6 of the time I'm going to give away $2. That actually balances out. One way to win 10, 5 ways to win 2. That kind of, yeah, it's overall, it's going to be fair. So that's what it means to be fair in a game of chance like this. Again, not necessarily what it means in English in everyday life. That's it. That's uniform distributions. Pretty straightforward. pretty easy. Um, the only thing now is to try some of these out and see if you actually recognize what makes them uniform. All right, I'll let you try those. Let me know if you've got any problems. Otherwise, I will see you tomorrow in what will be a much, much, much longer lesson than this one. Later.